right, let's start today's lecture. We have a lot of things to cover today. Hopefully we can get it done. Let's take a look at the calendar first, so we know what has been changed on the calendar. So today is September the 16th, and we have a new lecture to cover the two new tutorials, LEDs and SSDs. So the first one is pretty simple. I will just open that tutorial and show you some points on the tutorial to understand, make sure you understand everything. And for SSD, probably 80% of today's lecture will be focused on this part. It's something new is going to be covered in this tutorial. And if you look at here, homework 2 is due today. Did you submit your report online? Your HTML report? Okay, great. And for these two tutorials, they are due next Wednesday. Okay, so after today's lecture, spend some time on that. Make sure you can upload everything on time. Okay. So I'm going to show you what we are going to, so the main project need to be done in the SSDs in this tutorial. And I will let you know how and what you should do to make it happen. Let me plug in. Yeah. I don't have a, should be long enough. Okay, so this is the main thing you guys need to learn. So there are several techniques involved in programming a microcontroller. Like, so the 7-segment display is one of them. So after this experiment, you should be able to understand why do we need a digital system to control external circuits, because it's able to run fast. And this is a very fundamental display technique, probably invented 1,000 years ago. Since I don't have accurate numbers, just make up one. It's power consuming, and it's very inexpensive. So you can see the pros and cons by using this technique. And also, it is not able to display a picture, right? So whenever you are just simply trying to display a number, like the gas station, just showing you the price per gallon, or anything else, or the temperature in the swimming pool in the gym, right? It's good enough. And they don't care about power. But however, do you want to use this kind of device for this watch? The battery can only stand there for like 2 days. They want to use CC, no, what's the name of that? LCD, yeah. Liquid crystal display, right? Something like this, more power efficient. But this one is consuming power because every single bar is a LED device, right? So it's drawing a lot of current from the power supply. And also, if you want to display a complicated number, a series of number, you probably need a dedicated driver for it. We're not going to, use a driver for a complicated project in the future, but you have to take this kind of thing in consideration when you are designing a digital system, because whenever the CPU, because this is a 8-bit pretty basic CPU, only has one core, and that core has been occupied to do this display only, right? If you have any other tasks that you need this CPU to do, like sensing temperature or scanning push buttons, things like that, and you are not going to see a pretty smooth display like this, because it's taking time to do something else. And you do need a pretty homogeneously distributed time delay in between the different numbers for this kind of display. So it has 10 million cons and a few 5 pros. But we are somewhere still using this kind of display technology. But that's a good start to learning the digital system. Okay, and you need a shift register. Do you still remember shift register from logic? You probably forgot everything already. So shift register is this little IC device, and we're going to use a shift register to shift every bit to the output and do a serial in, parallel out to display a number here at one time. That's how that works. Okay, so the lecture is done, so we start with no. Yeah, I'm gonna explain more. So that's what we are going to do, and let's see how. Okay. Before we move to that one, let's take a look at the simple one first. The LED version. So LED stands for what? Yeah. So it's a diode. If it's powered up by a voltage, to let the current run through the diode, it's going to emit light. Okay, that's how that works. So the Arduino Uno board has a LED on surface mount LED on the board. I think it's being connected to the pin, digital pin number 13. So don't need to connect anything to the digital pins, and you can toggle that LED. So there is a LED blink example from the library you can directly use. You don't need to do anything else. Just you don't need to connect the board to anywhere because this is already shorted to number 13 on the board. And you open up that example and run it, and it's going to blink this LED. It's a surface mount LED. We can buy it. I have a lot in my drawer. So like this one, I think it's this one. Okay. Or you can also use a digital I/O pins to control an external LED like this. Keep in mind, so you have a lot of LEDs in your kit in the box. It has a longer pin, has a shorter pin. So the longer pin is anode, the shorter pin is cathode. So the higher voltage should be connected to the longer pin, and the shorter pin should be connected to a protection resistor and then to the ground. The reason you always need a protection or protecting resistor is the internal resistance of the LED is super tiny. Then whenever you connect the anode and cathode to the two sides of the LED, it has a really low resistance, which means there will be a pretty high current run through the circuit. Very likely it's going to burn down that LED. So you always need a protecting resistor. And the resistance, the value of the resistor is not really strict, right? So you can pick up anywhere from 200 ohms to 1K ohms. It's just limiting the current going through the LED. I think tens of ohms, things like that. Yeah. Yeah, it's very low. If you connect the 200 ohms resistor to it, then you get a brighter LED, right? Because it's lower resistance, which means higher current. If you connect a 1K resistor to it, then it's going to be dimmer. Depends on your need, okay? You can pick up 220, 300, 400, 500, 1K, doesn't matter. So this is a very simple example, just trying to let you test the digital I/Os of the Arduino. You just connect LED to any of the digital pins and blink it. Only takes you probably 1 second. No, a few minutes, right? 1 minute. So very simple examples like this one as well. So high means 5 volts, right? Low is 0 volt. So why high is 5 volts? Why is that? So here's a function in Arduino's IDE. You need to declare all these pins. So 2, 3, 4, 5, 6, they are the number of pins directly associated with the hardware. So when you are learning C++ or any other programming languages based on desktop's, you are not thinking about hardware. Right? You are not thinking about the physical pin on the CPU. But now you are programming embedded systems, so always think about the hardware. So the numbers 2, 3, 4, 5, 6, so they represent the real physical pins on the board. Okay, so I initiate an integer, and I call that LED2. Doesn't matter. You can name it whatever you want. And I assign number 2 to LED2. So now LED2 will be an integer variable holding number 2 in there. So whenever I'm setting up the mode in the setup function, so LED2 will be set up as output. So that's the mode for that pin. So mainly there are 2 functions. If you don't add another sub functions in the script, there will be 2 functions in the script for Arduino. So the setup function will only be executed for how many times? For once. That's how that was designed. Okay, so this will be only executed for once, and the loop will run forever. As long as you power it up, it's going to keep running this loop. So keep this in mind if you didn't know that. So you can set up the pin mode like LED2, which is pin 2 to output as output pin. So it's not receiving any digital signals. It's sending digital signal out to the outside world. Okay, that's how that works. So set up the mode for all these pins, and digital write is a function provided by the IDE, and you set up that pin to high. So high is how many volts? In Arduino, why is 5? Why it is 5? So any of the questions I'm asking in the class can be on the quiz, right, in the future. They are critical. When you're programming something, you need to know pretty much everything about the details, or you know what you are doing. Right? So if you put a high here, you are expecting 5 volts at this pin whenever you power it up. So the 5 volts will be delivered to here. If you have a multimeter, you test it, you'll see 5 volts. So my question is why it is 5 volts? Yes, but I just say high, right? So high. Why high is 5 volts? Why high is not like something else, you know? So what's the standard voltage for USB? So keep in mind, it's 5 volts. You are a either engineering student or computer engineering student. Definitely you should know that. During the interviews, they ask you what's the voltage for USB. You're like, So USB is 5 volts everywhere, 5 volts, right? So why somewhere for some of the microcontrollers, the logic level is not 5 volts, it's 3.3 volts. How can you make that happen? So one thing here, keep in mind, I'm going to repeat this in the future a lot, okay? So this is a digital device. You agree with that? Okay. It's, digital pins, high and low. Low is 0 volts, high is 5 volts. The reason you are getting 5 volts is because you plug in this one to your laptop. and your laptop is sending the 5 volts through the USB to your chip. Okay, and where does that 5 volts come from? From the laptop, the 5 volts. I didn't plug in my laptop to anywhere, right? So you know I have a battery in my laptop. So the battery is normally 12 to 20 volts, let's say 20 volts. So there must be a voltage regulator inside to step down that voltage to 5 volts to supply the logic, the digital chips, to supply the 5 volts to the USB. That's where the 5 volts come from, okay? And also the USB cord has a ground pin, a 5 volts pin. When I'm plugging this to there, to my USB port on the laptop, it's shorting the ground and 5 volts to my laptop, right? That's how you make the circuit. And the 5 volts comes in, is directly being shorted to the serial pin of the chip. So all the logic levels are at the same level because they have the same common ground. So 5 volts, 5 volts, 5 volts, 5 volts, like that. So that's how you part it up. However, for this jack connector, if I do not use, for example, I already uploaded my sketch to the Arduino Uno microcontroller, and I unplug this guy. Okay, since the code has been stored in the memory in the chip. Okay, and now I do not need any data transmission. Use the USB. I will just part up entire thing here from this part as a jack connector. And if you look at the voltage reading, it didn't show up here. But for example, is that possible? Like the voltage reading here is 4 volts to 12 volts. Is that possible? From 4 volts to 12 volts for this thing? When I'm trying to power up my Uno, would 12 volts work? You probably want to take a look at the voltage, the input voltage reading for your voltage regulator you placed on your PCB a couple weeks ago. Remember what's the name of the voltage regulator? EMS 1117. Okay, that's the little guy here. You use the same chip, so you just place the same device on your PCB in homework 1. Do you remember that? So that if you open the data sheet, it has a voltage rating for the input. It should be somewhere from starting from a voltage to a highest voltage, let's say 12 volts, for example. And if this is a 5 volts regulator, and if I give a 7 volts input, what's the voltage at the output of this regulator? Come on, it's a 5 volts regulator. I provide a 7 volts, you are expecting 5 volts, right? What about 8 volts input? Huh? It's still 5 volts. It provides a range, like 7 to 12. Okay, whatever the voltage, the input voltage is, it's going to give you 5 volts. That's how that works, right? That's the point of using this device. It's not really expensive and works really well. So if you have an 8 volts power supply, DC voltage, you plug in, you get 5 volts. If you have a 12 volts, you get 5 volts. If you have 4 volts, you get 5 volts. Really? If you have 4 volts, can you get 5 volts? No, this is a buck converter. It only step down the voltage. It's not a boost converter. It cannot boost the voltage. So 4 volts won't work. So you need something at least 6 to 7 volts. Why is that? Because all these regulators has a, it's called dropout voltage. Dropout voltage. So it's losing something, right? So if you have a 6 volts, if the dropout voltage is 1 volt, you're getting 5 volts, right? That's why it has to be at least larger than, you know, the output voltage plus the dropout voltage for the input voltage. Not clear? Let's say the dropout voltage is 1 volt, okay? And I do need 5 volts. So for the input voltage, it has to be at least how much? 6 volts, right? At least. But normally, if you are using a LiPo battery, 1 cell is 3.7 volts, so 2 cells will be 7.4 volts. That's the best option, actually. You just pick up a 7 point something volts, 2 batteries, put it in the cartridge, and pour out your toy. Okay? Works pretty well. So 7.4 volts is a really good option. So you can power up your microcontroller if you are using an AMS 117 5 volts voltage regulator. So plugging into here, 7.4 volts is going to regulate everything to 5 volts and power up your microcontroller. Okay. If you are not using a USB cable here to power up your microcontroller, you can also power it up using a battery, using an adapter. Okay, anything works to provide that 5 volts logic to your microcontroller. So if I'm using a 7.4 volts to power up everything, and if I use high here, what's the voltage level for high? If I'm using a 7.4 volts battery to power up from the jack connector, and when I'm writing high here, what's the voltage level at the output? 5 volts, because it's a 5 volts logic. All the clocks, all the digital signals inside the chip, in the CPU, is 5 volts. Because everything has been regulated at 5 volts. We just say it's a 5 volts logic. If it's a 3.3 volts logic, we just say it's a 3.3 volts logic. Okay, that clear? All right. Because you can write high or low to the I/O pins really quickly, and you can even make up a pattern of highs and lows at the output to form a protocol. Have you ever heard about this word, protocol? Protocol? Some of the sequential logic do need a specific pattern of highs and lows. You know, when you are connecting your smartphone to the Bluetooth speaker in the car, right? Why the receiver in the car knows your phone is sending request to it. Why it knows that? So for a different communication protocol, it needs a different highs and lows, a pattern, right? Like a conversation. So we're going to learn the details in embedded devices in the spring, but we also have a couple of experiments regarding all the protocols, like I2C, SPI, all these kind of things. They have a different pattern, but let's just think about this intuitively, right? So like Bluetooth, whenever you want to start a conversation with a receiver, what's the first step? Like when you are starting a conversation with a person, where do you want to start with? It's pretty much the same concept. How are you doing today? Like this, right? And good. What about you? Then you can start a conversation. That's a protocol. So you say something and they respond, and they will respect you, as they will expect you probably want to start a conversation, right? And then you say, hey, this is what I did today. I'm excited and I'm sad, whatever you want to say. And they will say something else. So, but you have to start a conversation first, like that. Sometimes it's also called a handshake signal. So whenever you are trying to connect your smartphone to the receiver device in the car, it actually has a signal, has a pattern saying, hey, like hi, for example, it's a code, right? It's a 101. right? And then you can have a if statement in the receiver, making a judgment. If I receive 101, I should acknowledge it. Then I'm gonna start receiving the data. If I'm not receiving 101, I'm not going to do anything. Just idle, just stay there, do not do anything. It's the same thing like when you are talking to a person, you say, how are you? They will start a conversation. Okay? It's the same protocol. But you can imagine there must be a digital circuit inside the device to detect that sequence. Like a state machine. If I receive one, I'm gonna see if I'm going to receive 0, jump to the other state. If it is 0, then jump to the other state waiting for 1. If it is 1, done. I will start this operation. Otherwise, I'm gonna come back to the initial state waiting for the first one. It's a state machine, right? State. Whenever all the states are satisfied, I know I'm receiving a signal. Somebody want to start a conversation. Then I'll start doing something. Okay, that's you are thinking about this kind of protocol from an intuitive level, which is good enough for this course since we are pretty much doing application focused, but not going down to any other the protocols of every communication method. Because some of the people, for example, for the I2C communication protocol, they'll spend like 2 years just using a hardware description language, Verilog, to write up that protocol for the entire 2 years. I got a master degree. It's not worth it. So let's just look at the application for now. And for the rest of the first tutorial, it's a lot easier. But I want to ask you a couple questions first. So like this circuit, if I do not push this push button, what's the voltage at this pin? If I do not push it, what's the voltage here? It's a circuit 1 problem. And you'll say 0. Yes. It's been a challenging circuit 1 problem for a few years. Is that 0 or 1 or 5? And why? You are saying, hey, it's disconnected. So I'm thinking it should be 0, but however, it's not. It's going to be 5 volts. And why is that? No current, then what? No current, no voltage drop. Is that correct? What is voltage drop? What is Ohm's law? Retake 201, please. So what is voltage drop? Can someone say what is voltage drop? Yeah, but what causes that? Yeah. Anyone can let me know what is Ohm's law? Anyone can be the hero? Tell me what is Ohm's law? Anyone? Ohm's law. Ohm's law. Yeah, but describe it. If you got a resistor, current runs through the resistor, you get a voltage drop. That's Ohm's law, right? That's it. Resistor, run the current through the resistor, you get a voltage drop. And the voltage drop equals to IR. That's it. That's Ohm's law, right? So, is there any current runs through this circuit? It's disconnected. There's no current. So, 5 volts, no drop, 5 volts. Is that clear? And the resistor here is called pull-up resistor. Pull-up. It's thinking like someone is pulling up this pin to VCC. Pull up, right? So that's why you can get a 5 volts at this pin. If you connect a resistor to this pin to ground, it's called pull down resistor. It just pulls that pin down to ground. Okay, keep in mind, memorize this two concepts. So like this one, if I do not push this push button, do you expect LED to be on or off? If I do not push it, come on, guys. On, right? Why? Because it's 5 volts. It's a high potential, low potential, and current will run through the circuit, run through the LED, and light it up. So there are several experiments. You just work on that and report it in your HTML report. Now let's take a look at SSDs. So probably we won't be able to cover everything today. We don't have time. It's a little bit complicated. Let me try to not covering every single detail so you can guarantee you can get started, since next time will be Friday and you won't be here and you don't want to wait until Monday, right? So Wednesday is going to be still on Wednesday next week. So here is the SSD 7-segment display unit in your box, and it has literally how many? Eight LEDs inside. So it's called 7-segment, but why 8? It has a point, a decimal point. So total 8. Okay, total 8 LEDs in different shapes. And there are 2 types of SSDs on the market. You probably will see. And if you see everything, all the cathode are being shorted to one pin, it's called common cathode SSD. Otherwise, they are common anode SSD if they short all the anode together. So do you know how that works? If you just look at this circuit, you can control every single anode over here. If you give a logic high or low, you can light up that LED. High or low. Let me know. High or low. Like I want to turn on 7, turn on A. Should I give a high or low at 7? Here is a common cathode. So I'm going to ground the cathode. I will ground the cathode. So I need to give a logic high, so current can run through the LED, go to the ground, and turn it on. And you can control each one individually by yourself. So there are several ways to turn it on and off. Okay. For example, I just don't want to use any drivers, any ICs. What I can do is I just plug in this guy on the breadboard. Do not forget to connect a resistor to protect it, like this. I have a quick quiz question for you. Look at here. Do I have 8 resistors? No. What's the difference? So what I did over here is I only have one resistor connect to here and to the ground. So if I only do that, can I still protect all the LEDs? And why? Yes, I can. Why is that? Because that's the only way the current can go through in the circuit. No matter which one is turned on, they have to go through this critical path, go back to the ground. So if I put a resistor here, it should be able to protect everything. So what's the issue if I do that instead of doing this? What's the issue? Higher resistance, yes. And what else? So think about that. I have only one resistor here, like 1K. If I turn on, for example, I have different displays, right? Like 1, 2, 3, 4. They have different numbers of LEDs to be turned on. So which means if I have different numbers of LEDs to be turned on, I'm going to have a different brightness for different numbers. 8 will be the brightest or dimmest. Think about it. Should be the dimmest, right? Same current. Right? So the current is being shared by all the 8 LEDs. So if you do this, you probably will see a more homogeneous brightness for different digits. But I did this one because before the class, I just connected this circuit a couple minutes before this class. So want to make it fast, which is fine. And you couldn't actually see the very significant difference of the brightness for different numbers. It's not really obvious, okay, which is fine. So what I used here is a 1K resistor, and it's going to be able to do the job. If you do not want to grab like 8 220 resistors, you can just do this. Just 1K, connect it to here, so you can remove all these other resistors. That making sense? Which is fine. That's okay. So see what I did in the past. I have 8 220 resistors being connected to every LED. But you don't have to do that. You can just connect one to here. So if you look at the pin out for this device in your box, so COM is a common cathode. So this pin, they are internally shorted actually. So you don't have to connect both to the ground. You just need to short one to the ground. Before you short it to the ground, do not forget to connect a 1K resistor in the middle, so you can protect the LEDs. So like from here, a 1K resistor, ground. Done. You don't need any other resistors. Is that clear? Okay. So there are a couple ways to turn on this guy. You'll see I have Arduino here, but actually I'm not using the CPU at all. So I told you I can manually display a specific number on the SSD unit. So what I used here is I only use the 5 volts power supply of the Arduino board and a ground pin here. So I'm just using this guy as a power supply, but nothing else. So I power up the breadboard and ground the breadboard, and I will just specifically turning on off specific LEDs to make up a number. Is that clear? So you can turn on different bars to form a number, right? So this is for the first example. But however, the disadvantage is you couldn't change it since it's already permanently shorted to the power or to the ground. So you couldn't change the digit. The reason you want to need a microcontroller is you can always change it, you can program it, right? So this is just something useless. Unless it's a permanent number to display. But that's super rare. Right? And the second way to do that is to use a decoder. If you do not have the decoder in the box, which is this chip, the IC chip, looks pretty much the same as a shift register. If you don't have it, let me know. I can give you one. So the reason you want to use a decoder is you can reduce the pins, the number of pins being occupied on the board, because you only need 7 inputs, battery inputs, to form 8 different types of output. So just provide a binary code and it's going to decode it. And I believe you designed a decoder in the logic class, right? And you have forgotten that. I'm pretty sure. So just look at the videos and lecture notes if you like to see how the decoder works. You can design it by yourself. Actually, it's super simple combinational logic circuit, no problem. So the last one is the best option, which is a shift register circuit. That's the IC chip. You should have it in your box. And this is the most complicated one in these two tutorials. And it takes time to explain this, but let me do a brief introduction first. And what I can do is I will probably give you a link to the class I covered actually in this spring this year. So you know how that works. But let me start explaining this really quickly. See if we can do that. So the first thing you need to do is look at the pin out of this chip. So it has all these A, B, C, D, and E, A, B, C, D, E, F, G, H. So all these output pins, and they should be shorted to the SSD unit. So let me do a snapshot to the SSD, and it's easier to show you. Okay, so A, B, C, D, E, F, G, H. Where are they? Did you see that? It has a specific order. So A is the top bar, A, B, C, D, E, F, G, H. So here's H. Okay? And you have to look at this guy to find out which is which. So this pin controls A, which is this bar. B controls this guy, so on and so forth. Okay? And you need so because the shift register have all these pins, so you just want to connect A to A, B to B, and H to the point, right? So that's the point, and G to G, so on and so forth. So these are all the output pins. What about others? What about the other ones? So like these ones. 5 volts, ground, no problem. And SER, SER means serial. So that's the serial input. Serial input. It's a serial in, parallel out shift register. All right. And so here's OE means output enable. And if you see a bar on the top, which means low, voltage low will enable that. Remember the bar on the top means not, right? So inverting the result. So it's actually, you have to give a voltage low or logic low to enable the output. That's what you need to do. So this one is a something clock, right? And this is another clock. And that's a clear. So if you connect this pin to ground or high, it's going to clear out the output. So now let me know, should that be ground or high in order to clear everything? Low or high to clear everything? Low, because there's a bar on the top, right? Remember, whenever you see a bar on the top, it's gonna enable that function when it's grounded. Same here. If you want to enable the output, ground it. If you want to clear everything, ground it. Otherwise, pull it up to the high voltage high or logic high. Okay, and this is not used. Don't worry about that one. So the way that works is, look at here. Look at the circuit first. Okay, I'm going to explain this to you. I'm going to send you a link. We don't have time. We don't have Friday to explain this. So I have a video to explain everything in detail. But now let's take a look. It has two stages. I know there are a lot of blocks. I understand it, but it's pretty simple. Let's just look at it. So the first stage is a shift register. Serial in. So SCR is a serial in. It's just one line. That's why it's a serial, not parallel. So the binary data is being pumped into this line one by one. So like you have a 1 here, and it's going to be transferred to the output of the D flip-flop, and it's going to stay here. And whenever the next clock arrives, which is the SR clock here, it will send that data, which stayed at the D flip-flop's output, to here. Whenever clocks arrives or the rising edge arrives, it's going to transfer this data to here, and then so on and so forth. So it's actually shifting whatever is being pumped to here in order. So what this circuit does is this clock, the SR clock, is shifting the data at ICR. Don't worry about why. Watch the video, you'll be able to know why. So data comes in. Let's think about it. So this is a digital system running really fast. But let's slow everything down. And we just think about that, okay? So now ICR data comes in. It's a logic high, okay? It's waiting there. It's waiting there. Before you have a clock, the SR clock rising edge, nothing will be transferred to the output. Okay? Whenever SR clock has a rising edge, boom. So that data will be sampled and be transferred to this output. Because this is the same wire, so it's going to waiting here for the next SR clock's rising edge. And then after, so whenever the next SR's rising edge arrives, it will be transferred to here. And then waiting here. And then another rising edge, boom, boom, boom. Is this being shifted? Is that data being shifted? Yes, it is. So think about, you have a series of data. So data comes in like this, 1 0 0 1 0. Okay, that's how the data was taken in line. So 1 comes in first, and after the SR clock, boom, 1 is here, and 1 is also here because it's the same wire. Another SR clock, boom, 1 comes to here. And because the SR clock is being shorted to all the clock input for the flip-flops, so the next data is 0, so 0 will be shifted to the output of the first flip-flop. All right, so 1 0 1 0. Then 1 0 0, right? 1 0 0. That making sense? Even a little bit? Okay, I'll send you a link so you know how these flip-flops works. But now just think about, I just let you know the way it works. So if you want to look at why, watch the video, okay? So 1 0 0, because this data, the pattern is 10010, right? After 5 clocks, the data after at the shift register will be 10010. So it's going to be 10010. Is that correct? It's being shifted. So it looks like this. So just imagine a figure, right, or animation. So there are a series of data comes in, boom, 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 like this. Here's a clock, right? Doom, 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 pumping all this data to the shift register. So data comes in series, in serial, so one line, like this, boom, 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 and then go downwards, being shifted downwards. So like this, being shifted downwards, and so the data are ready here, waiting for the final clock, right? So data are ready here, and then boom, to the output in parallel. Is that clear? It's running super fast. So boom, 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 boom. Ready? Boom. Like this and this. That's how that works. So you are not having a lot of, so our clock is a final clock to make everything happen, to output all the data waiting there to the final output in parallel. So it's actually waiting for this clock. However, it does need 8 rising edges to pump all the data in serial for the shift register. That's how this circuit works. And when you are connecting everything to the shift register, so like what I mentioned, so A to A, B to B, C to D, C to C, all these ladders, just connect them to the SSD module respectively. And ICR should be a digital pin on your Arduino. OE should be connected to a pin on Arduino. But what are they? So let's take a look at the example code here, or the example schematic first. So here's it's not clear. It's from the document, actually from the example of the kit. So it's not super clear. Let's see. OE. Is this OE? Where OE is being shorted to? You can see a black line to the ground. Is that making sense? Why to the ground? Why OE to the ground? What is OE? Output enable. So you want to connect output enable to ground so you can enable the output. Because if you look at the OE, it has a bar on the top. So which means ground will enable it. Okay? If there's no bar, then 5 volts will enable it. I know there's a lot of information to be covered today and kind of new. All right, that's OE. And ST, so R clock to one of the pins. I'll show you where is that. And I start clock not. You don't want to disable it, so it should be VCC. I don't think we have this pin on your chip. So let's look at the code. Declare the pins you want to use for R clock, SR clock, and ICR. So pin number 11 is being used as an R clock. So R clock is a final clock, pump everything out in parallel to the output. SR clock is every single clock, pump every single bit to the shift register. So you assign number 11, number 9 for these 2 pins. And the data pin is number 12. Okay, so number 12 should be shorted to the ICR pin on the shift register's IC chip. And here's example code. One thing you need to know is there are two options to pump the binary data to the shift register. One is called, because the shift out function is embedded into the Arduino's IDE, feel free to use it. It's going to do manage a protocol for you, so you don't have to manage every pattern, every high and low in the protocol. It's complicated. It's not worth it. So you are using shift out function to do that job. So this function defines the data pin, which is the ICR line. So you need to tell the Arduino where is the data pin you are using for the shift register. And clock pin, which one is being used as the clock pin. So after you tell Arduino which pin is the clock pin, it's going to send the ICR clock to that pin on Arduino. And here's MSB first. So here's the option you can use MSB first or LSB first. So I already provided the MSB first sketch for you, and I'm going to let you modify the code and using LSB first. So what's the difference here? Since you are going to have a binary data, it's an 8-bit binary data because this is in hex format, right? So for hex format, every single digit represent how many binary bits? For hex? 4. So 3F actually means, look at the address column here. 3F is actually a binary number, right? It's going to be 0011 and 1111. Okay, so it's an 8-bit binary number. It's here. And if I'm using MSB first, it's going to shift the MSB first and then followed by all the other digits. That's important because if you have a number like this and you know it is shifting the MSB first, and you can expect finally what are the numbers are going to waiting to be pumped to the output. So remember this one, just 1 minute, okay? Remember this one, 0011, 111, and MSB first. So if you define MSB first for this sketch, then 0 will be pumped out first at the ICR data line. So like this, right? So remember the order when how that works. So here's a shift register, right? You have an ICR line, the data line, and you have a clock, like boom, 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 doing this. So everything is ready. Then boom. Okay, that's how that works. If you are doing MSB first, let me know. Okay, 8 bits. Okay, 8 bits. What is this? What is this bit? What is this number here right now? What is this number? Right? What is this number? If I'm doing MSB first? 0. Why? Because the first number is going to the bottom. Is that clear? You have 0011, 1111, right? MSB first means 0 will be shifted to the bottom because it comes first. So what is this number? 0 as well. What about this 4? All ones. Okay? So since you connect A, B, C, D, E, F, G, H to the SSD module, so A will be what? A will be 1. H and G will be 0. Right? Is that clear? You get a pattern. You get a pattern. So you know it's going to display a number on the SSD module. So let me know if I have, for this sketch, if I have 3F, right? Like the one I just showed you, 00111111. If I have this number, then what's gonna be displayed to the SSD module and why? Take a look. Take a look at this guy. 0, why is that? G and H are off. So this bar will be off. This point will be off. All the other ones will be on. That's why 3F will do the job. Is that clear? That's just one example. Can you just display different numbers? Like 1, 2, 3 until 9. Same concept. Easy. However, I have a task for you guys. I already gave you the sketch for the MSB first. If you change that one to LSB first, just change M to L. Okay, just change that little thing in the sketch. And have to modify all the hex number code to display 0 to 9. You can imagine that, right? So that's your job. Change M to L. So it's going to be LSB first. All right? Then change all this hex code accordingly to do the same job. Display 0 to 9. That's what you are going to do. And there's one thing you need to know, which is whenever you are trying to update the shift register, you need to give a low and then do the shift L function and give a high. So which will create a rising edge. Low first, high, right? You got a rising edge to make it work. So the latch pin is the R clock. Is that making sense? So everything is being, so the shift L function is going to shift everything to the shift register and waiting there, and give a high, boom. That's how you update everything. Clear? All right. I will send you a link for the video where I explained the flip-flops. If you need to watch it, just go ahead and watch it. Till next Wednesday.